In experimental modal analysis, we do not normally need to measure the full frequency response function matrix. In the ideal situation, in fact, it's only necessary to know one column or one row of the frequency response function matrix. So that poses another question. Should I measure a column by moving the response transducers, or shall I measure a row by moving the excitation force? This presentation will focus on this kind of issues. So in this presentation we are going to discuss the topic of roving response measurements or roving excitation measurements, because these are two different methods to measure a row or a column of the frequency response function matrix. So let us assume we have a cylindrical test object with observation points from 1 up to capital N. And let's also suppose that we are going to measure the frequency response function between exciting force and the responding acceleration. And we have 4 synchronized measurement channels at hand for the measurements. So let's assume now that we have single degree of freedom excitation. Let's, for simplicity, put it in point 1. And we have 3 response degrees of freedom indicated here. So we have 3 perpendicular directions: an x direction, y direction, and a z direction. So from the definition of the frequency response function, we know that the frequency response function is the ratio of the frequency spectrum of the acceleration over the force, exciting force. And note now that the sort of boundary condition is that all other forces except the one we use to excite the system should be equal to 0. So when we use roving excitation and fixed response method, then we can start with exciting point 1, and when we measure the frequency response functions with our 4-channel system, we will get 3 frequency response functions. We will first of all obtain the frequency response function hnx1, that is the acceleration in x direction in point n over the force, exciting force in point 1, and so on. So 3 frequency response function per measurement is what we will go to achieve with this method. If we excite point 2, then we obtain another set of 3 frequency response functions, but with a different excitation point now, of course. So when we have spanned all n excitation points, then we will have a set of 3 frequency response function rows in our frequency response function matrix. So each one of these rows corresponds to 1 fixed response measurement. So let's say we organize them like this as row vectors. In the other alternative, when we use a roving response and fixed excitation, let's say we excite point n, and we start with a response in point 1, and then we span all n measurement points. Then we will end up with 1 single column of the frequency response function matrix. So instead of 3 rows, we get 1 column. So to compare now, 3 rows in the frequency response function matrix or 1 column in the frequency response function matrix? Are these equivalent? Do they contain the same information? What are the pros and cons, advantages or disadvantages? Are they equivalent? No, they are not. First of all, if we use the Roving excitation method, we will get 3 times n frequency response function in 3 rows. If we use the alternative, that is Roving response with a 3-axial accelerometer, that will give us the same amount of frequency response functions but in one single column. And that has important implications for our results. Let's start now with the Roving excitation, where we get 3 frequency response function columns. Well, the advantage with this, the main advantage I would say, is that the risk of missing modes due to placing the fixed point, in this case the fixed accelerometer, on a node line of a mode is very small. There is a risk, of course, but the more columns we measure, the smaller the risk will be. So that is the main advantage of Roving excitation. Another advantage is that the test object will be, well, it will not change. It will be invariant between the measurements. Well, in this case, I assume now that we use the hammer excitation. And the reason for this is that the alternative method, then you move the accelerometer. So actually, the test object is changed between the measurements. In this case, we have the same test object, since the accelerometer is fixed in one single point. The disadvantage is that when we use hammer, and also shaker by the way, then we have to stick to one single degree of freedom for the excitation. If we use hammer, then the exciting force is bound to be normal to the test object surface. So when we hit with the hammer, we apply a force that is normal to the surface. And that is, as will be shown later on, a disadvantage of this method. So that means actually that we will have no information on tangential mode shape components in the final results when we have extracted the mode shapes. And that, of course, makes it difficult to interpret the mode shapes. When we animate the mode shapes, we will have lack of information that makes it difficult to understand how the mode looks like, what deflection shape the mode has. Now, if we go to the other alternative, Roving response, fixed excitation, the advantage now is that we have actually 3 times more frequency response functions per column. And that means, in fact, that we have 3 times more information on each mode shape. And also, in this case, if we have the 3, translational directions, x, y, z, all these directions will be represented in the observation points. And that means, in the end, also in the mode shapes. And that means that the mode shapes, if we have performed the measurements correctly, will be without distortion. So, for instance, as an example showing this, consider, let's say we have a beam with a cross section that is circular. So this is the cross section. And if we now consider a bending mode where the cross sections moves up and down in the vertical direction like this, and also suppose that the cross section deformation is negligible. So, and also suppose that we have a set of observation points 12 observation points around the circumference of the circle like this. And first, let's assume that we have this Roving triaxial accelerometer and the fixed excitation. So let's say we pick this point for the excitation and we move the accelerometers around in all observation points like this. Then we have, in the end of the measurements, we have one column with 36 frequency response functions in this case. And the important thing here is that all translation degrees of freedom is represented in this frequency response function column. So if we now animate the motion of the circular cross-section, it will look something like this. As you can see, it's, as expected, undeformed, and it moves up and down around its undeformed state. The other case, if we instead use the Roving excitation and fixed response method. So in this case, we let this point be fixed and we move the excitation around. So this will now give us 3 rows of the frequency response function matrix, and most important, the exciting force will always be normal to the surface. So that means that when we have extracted the modes, and in particular this pure bending mode with negligible cross-section deformation, then it will look like this. And as you can see now, okay, the center of the cross-section moves up and down, but the shape of the cross-section is deformed. And that is, of course, due to the lack of tangential deformation components in the points here. So in this case, only this point and that point moves correctly. All other points suffer from this loss of information, and in particular these 2 points. Since these 2 points are moving in the vertical direction like this, we cannot capture anything about their motion when we look, since we look in the normal direction. So, what about the disadvantages then of this Roving response fixed excitation technique? Well, the disadvantage is that the test object varies between the frequency response function measurements. If the accelerometer is of low mass compared to the test object, then it doesn't matter. The influence on the results, measurement results, will be negligible. But if we have a lightweight structure, test object, then this can be important. The second disadvantage is, of course, that there is a risk that we lose information on one or more modes due to the fact, well, that there is a small risk that we locate the fixed excitation point on one or more modes, modal lines, and those modes will be missed. So, in the end, which alternative should I choose in a given situation? Well, as you have understood, I suppose, that is a trade-off between if you need in the end the results, a complete list of modes, or accuracy in the mode shapes. So what property of these 2 is the most valuable in your given situation? That is what
decides your choice.